Okay, let's unpack this. Imagine peering into the cosmos and finding things that simply shouldn't exist according to our best theories. Today, we're embarking on a deep dive into a collection of recent astronomical discoveries that are not just fascinating, but, well, genuinely baffling scientists and pushing the limits of our understanding.
Yeah, it's fascinating how new data often doesn't just fill in gaps, but forces us to question the very foundations of what we thought we knew. These aren't just anomalies, they're like signposts to entirely new physics, new phenomena. We'll explore 3 cosmic enigmas that are challenging astronomers right now, from an impossibly stable radio signal to explosive events that defy explanation.
Okay, so first up, this enigmatic 22-minute signal, GPMJ 183910. It's a persistent mystery. It was initially picked up in 2022 by the Murchison Wide Field Array, right? But then, amazingly, they found it hiding in old data going all the way back to 1988.
35 years. That's incredible.
Yeah, exactly. 35 years. It's about 18,000 light years away. And the pulses, they last between 30 seconds and 5 minutes. And they show up in this really precise window, like 6.5 minutes wide, centered exactly 22 minutes after the last one.
Rhythmic pulses. Sounds familiar.
Right. Your first thought is pulsar. It ticks so many boxes. You know, pulsars, these incredibly dense neutron stars, super strong magnetic fields, sweeping beams of light like a cosmic lighthouse.
Yeah, the classic model.
Yeah.
A teaspoon weighs, what, 11 times the entire human population?
Yeah.
Just mind-boggling density.
Totally. And this GPMJ 183910, it shows the classic signs. Radio waves, strong polarization, those distinct 90-degree shifts in polarization. So much of the data points to a pulsar, you'd think it was an open and shut case.
That's where it gets weird. If we connect this to the bigger picture, the problem is its rotation speed and stability. Typical pulsars spin super fast, maybe 10 times a second, down to maybe once a second. GPMJ 183910 is once every 1,318 seconds.
Wow.
Yeah, over 1,000 times slower than a typical pulsar.
So it's way too slow then.
Way too slow. We have this concept called the death valley for pulsars. As they radiate energy, they slow down. Eventually, they slow so much they can't sustain the process creating the radio beams. They just switch off.
And GPMJ 183910 is where relative to that?
It's way below even the lowest line marking the death valley. I mean, according to our theories, it should be well and truly switched off, dead silent. Yet, here it is, pulsing away for at least 35 years.
And it's stable too, right? That's the other kicker.
Exactly. Over 3.5 decades, it's slowed down by less than 0.3 milliseconds. Tiny. That kind of stability in something rotating so slowly, it just doesn't fit anything we know about pulsar evolution.
Okay, so if it looks like a pulsar, sounds like a pulsar, but can't be a pulsar by the known rules, what else could it be? What other ideas did they look at?
Well, they went through the possibilities. One idea was a magnetar, neutron stars with these insanely strong magnetic fields. They have starquakes.
Right, those explosive events.
Yeah, but starquakes are temporary. A few years, maybe? Not 35 years of steady pulsing. Plus, you'd expect to see powerful X-rays in nothing. No X-rays detected from this source. So magnetar is pretty much out.
Okay, no magnetar. What about a highly magnetic white dwarf? Could that do it?
Another good thought, but that runs into trouble too. You'd need a magnetic field way stronger than any white dwarf we've ever seen, like orders of magnitude stronger. And the only radio pulsing white dwarf we do know is AR Scorpii, and it's about 1,000 times fainter, less luminous than GPMJ 183910. So that doesn't quite line up either.
And other stuff like stars interacting with planets or binary brown dwarfs.
Yeah, they considered those too. But the problem there is the sheer power. Those kinds of interactions produce radio waves, sure, but they're typically something like 100 million times weaker than what we're seeing here.
So in the end, it seems like none of our current theories can really explain this 22-minute signal.
Pretty much. And that's not frustrating. It's actually exciting. It means this signal, whatever it is going to shed light on emission processes beyond the neutron star death valley. It's pointing towards an entirely new phenomenon. We might need to rewrite some textbook chapters.
Wow. Okay, from a pulsar that refuses to die, let's shift gears to the Minga. This one went from just a mysterious gamma ray haze to, well, a cosmic antimatter factory. It started back in 1972. NASA's SAS-2 satellite spots this unknown gamma ray source in Gemini, and they called it Gaminga, kind of a pun meaning it's not there in a Milanese dialect because It was so elusive.
It really was. It's fascinating how long that mystery lasted. The source was hidden for decades until, the technology caught up.
Right. It wasn't until 1983 they found a weak X-ray signal. But the big step was 1991. Rosat and Egret, two different satellites, both confirmed pulsed X-rays and gamma rays, a period of 0.237 seconds flashing 4 times every second. Suddenly, Gaminga behaved like a pulsar.
Okay, but that raises a question. If it started acting like a pulsar, why was it initially radio silent? And why didn't it seem to have a nebula around it like other famous gamma ray pulsars, say the Crab or Vela?
Good questions. Well, the radio silence, turns out we just weren't listening correctly, apparently. In 1997, they finally found extremely weak pulses, but only at a low frequency, around 100 millihertz. Most earlier searches were looking at higher frequencies, like 400 to 600 millihertz, and theory suggests Gaminga's magnetic field might actually absorb or bend those higher frequencies away.
So it was transmitting, just not on the channels most people were tuning into. Makes sense.
Exactly. Turns out Gaminga wasn't truly hiding. We just weren't using the right cosmic radio station. And we now know something like 99% of its energy comes out as gamma rays. It's one of the brightest gamma sources in the whole galaxy. It's the remnant of a huge star that blew up maybe 350,000 years ago. And that missing nebula, they found it in 2005, a pulsar wind nebula, basically a shell of gas around it.
And this thing is moving, right? It's not just sitting there.
Oh yeah. Here's where it gets really interesting. Gaminga is a proper rogue star. It's tearing through the galaxy at almost 210 kilometers per second. That's unusually fast. From our perspective, it moves about 0.2 arc seconds across the sky each year, like a cosmic cannonball, really.
That speed is incredible. And it actually creates these two ghostly X-ray tails stretching out behind it for like 3 trillion kilometers. It's like the weight from a boat, you know, caused by its sheer speed and rotation compressing the gas and dust it's plowing through. And remember, this thing has the mass of 1.5 suns squeezed into maybe 20 or 30 kilometers across. The density is just immense.
And its orientation matters too, doesn't it? How it's pointed affects what we see.
Absolutely. The idea is, think of its emission like a donut, a torus, around its equator emitting gamma rays, and then jets coming out the poles emitting radio waves.
Yeah.
For Gaminga, that gamma ray torus seems to be pointing right at us. That's why it looks so bright in gamma rays. But the radio jets from the poles, they're pointing off to the sides. So from Earth, it looks radio dim. It contrasts with other pulsars where maybe the jet points at us, making them radio bright, but gamma dimmer.
Sometimes the most simple explanation, like just how it's tilted, is the right one.
Exactly.
But the really big story with Gaminga connects back to something else entirely, this strange abundance of antimatter hitting Earth, specifically positrons. The AMS-2 detector on the International Space Station has been picking up more positrons than expected since 2011.
Right, and that was a huge puzzle. For a while, people were really hoping maybe this is a sign of dark matter annihilating or decaying. You know, the hunt for dark matter is a huge deal in physics.
Sure, the smoking gun everyone's looking for.
Exactly. But then, in 2017, data from the HAWC Observatory found this small gamma ray halo around Gaminga. That was the first real observational hint that maybe a pulsar could be the source. Pulsars are known to create electron-positron pairs in their magnetospheres.
And then came the clincher, right, with the Fermi telescope.
Yes. New data from Fermi's Large Area Telescope looking at lower energy gamma rays revealed this spectacular glow. A huge oblong halo around Gaminga, stretching 20 degrees across the sky.
20 degrees? That's massive, like the size of the Big Dipper.
Yeah, it's enormous, even bigger at the lowest energies, maybe 40 times the area of the full moon. It's a vast cloud of positrons escaping the pulsar. And the calculations suggest this one pulsar, Gaminga, could be responsible for maybe up to 20% of all those extra positrons we detect near Earth.
Wow, 20% from just one source.
Yeah, it's a magnificent revelation. It basically solves, or at least provides, a major part of the solution to that decade-long antimatter mystery. The rest probably comes from other similar pulsars. So it looks like we don't need exotic dark matter to explain this particular excess. It's these amazing cosmic particle accelerators doing the job.
Okay, that's incredible. So from a weird pulsar and an antimatter factory, let's get to our final enigma, luminous fast blue optical transients. LF-BOTS for short.
LF-BOTS, yeah. These are something else.
Okay, let's unpack this. Imagine an explosion maybe 100 times brighter than a typical supernova. But instead of fading over months, it flashes and disappears in just a matter of days.
That's the essence of it. They have some shared traits.
Right. They're predominantly blue, extremely luminous optically, bright in X-rays, UV, radio, and they're fast. They ramp up to peak brightness and dim down really quickly, hours to days, totally unlike supernovae that take weeks or months to fade away.
The first one really caught everyone's attention. AT-2018 Cow, nicknamed the Cow, detected in Hawaii in 2018 by the Atlas telescope. Like you said, 100 times brighter than a normal supernova, gone in days. It was pretty far, 180 million light years away.
And they initially thought it was a supernova, right? A specific type?
Yeah, they classified it as a Type 1b supernova at first, but something about this explosion didn't quite fit. When they looked closer, the spectrum showed these unusually broad emission lines and very little helium, which was odd for one day.
It just appeared so fast.
Appeared out of nowhere in days, way brighter than expected, 10 to 100 times brighter. And the explosion itself seemed really asymmetrical, lopsided. Researchers called it the most spherical explosion ever seen. So whatever the Cow was, it started to look less and less like any kind of supernova we knew.
Okay, so one weird event, but then more started showing up. The koala, the camel.
Right, and these first few, including the Cow, all seemed to happen inside the spiral arms of galaxies. That seemed to fit initially with the idea of a core collapse supernova. You know, massive stars tend to be born and die relatively quickly within those star-forming spiral arms. It looked like a pattern.
A nice, neat theory taking shape.
Exactly. But just as researchers felt they were getting a handle on it, the universe decided to surprise them again.
Of course it did.
In 2022, they found the Tasmanian Devil. And this one didn't just fade once. It produced repeated bursts, equally bright, just minutes apart. 14 different telescopes confirmed it. It looked like a star trying to die, then reviving, then trying again, over and over.
A star that keeps dying. That doesn't sound like a supernova at all.
Not remotely. That really threw a wrench into the core collapse idea.
And then came the final nail in the coffin for that simple theory. The Finch.
Ah, yes, the Finch. April 10th, 2023. This is maybe the biggest blow yet. This LF bot was way out there, 3 billion light years away. But the kicker, it was 15,000 light years from the closest galaxy.
15,000 light years, so totally isolated.
Completely solitary, just out there in the void, in the middle of nowhere. That was a huge problem for the core collapse theory because massive stars just shouldn't be found way out there, far from any galactic nursery.
Okay, so if it's probably not a standard massive star exploding in a galaxy, astronomers had to go back to the drawing board, right? What are the new leading ideas, especially for something like the Finch?
Pretty much. Two main alternatives are now on the table. One, maybe it's a star getting torn apart by an intermediate mass black hole, an IMBH.
Intermediate mass, so bigger than a stellar black hole, smaller than the supermassive ones in galaxy centers.
Exactly. Hundreds to maybe tens of thousands of solar masses. They're still theoretical, mostly. We haven't definitively found one. But simulations show that if a star gets too close to an IMBH, it gets shredded. Tidal disruption event. And the model suggests this could fling matter outwards at maybe 10% the speed of light, producing something as bright and fast as an LF bot.
And could these IMBHs be located far from galaxies?
Well, one idea is they might lurk inside globular clusters, these old, dense clusters of stars that often orbit in the halo of a galaxy, far from the main disk. So an IMBH in a globular cluster could explain an explosion like the Finch, happening way out in the galactic boondocks.
Okay, that's one possibility. What's the other main theory?
The other is a kilonova. That's the explosion you get when two neutron stars collide and merge.
Right, those create huge explosions and gravitational waves.
Exactly, massive blasts. And they should produce a specific gravitational wave signal, a chirp, that detectors like LIGO can pick up.
Why?
Now, as luck would have it, when the Finch went off, LIGO was actually down for maintenance.
Oh, tip.
Isn't it always the way? So no gravitational wave confirmation for that one. Also, we didn't detect a gamma ray burst, which often accompanies kilonovas. But it might have just been too far away for the gamma rays to be seen. So the kilonova idea, the data is still inconclusive. It's still on the table.
So how do we figure this out? How do we solve the mystery of the Finch and these other weird LF bots?
Well, one key step is planned observation. Astronomers want to use the James Webb Space Telescope, point it near where the Finch happened, and look really closely for any faint globular cluster. If they find one, that would definitely boost the IMBH theory.
Then longer term.
Longer term, the big hope is the Vera C. Rubin Observatory. It's set to come online around 2025. It's going to survey the sky much wider and deeper than before, capturing maybe 10 times more light. It should find many more LF bots.
Ah, so getting a bigger sample size might reveal the patterns.
Precisely. More examples will help us see if things like the Finch are common or rare, if the repeating bursts of the Tasmanian Devil are typical or not. It'll give us much better statistics to test the theories. These are genuinely super new phenomena. They keep surprising us, which just goes to show how much we still have left to learn about the most extreme corners of the universe.
Okay, so we've journeyed from a pulsar that refuses to die, defying our understanding of stellar physics, to a cosmic antimatter factory hiding in plain sight, explaining weird particle showers on Earth, and now to these unbelievably bright, fast explosions that are rewriting the rules of stellar death. What an incredible deep dive into the real cutting edge of cosmic mystery.
Yeah, if we connect this to the bigger picture,
Yeah.
it's just so clear that our universe is far more complex and frankly more surprising than we often give it credit for. Every time we build better telescopes, push our observational limits, we seem to uncover these new unknown unknowns, things that just completely challenge the textbooks and really spark revolutions in how we think about everything.
Absolutely. It's that thrill of discovery, isn't it? That feeling of knowing there's always more out there, more to figure out. It's what keeps us looking up, asking those big questions. So, as you think about all this, maybe ponder. What do you think is the biggest secret the universe is still hiding from us? And how might these baffling new discoveries, these LF bots and weird pulsars, actually pave the way for entirely new fields of astronomy we can't even imagine yet? We invite you to keep pondering these cosmic questions.